Welcome to the introductory video about torque and static equilibrium. I'm going to try to make this one a little bit quicker than we have in the past, so stick with me. The first thing we want to talk about is torque, and here's a short little clip which I think gives a pretty good definition of torque.
Torque is different from force. Force is how hard you need to push or pull an object to move it in a straight line. Torque is the amount of effort used to rotate an object.
Alright, so that was just a little animation. Torque causes rotation. Just like force causes linear motion. A force, when it's applied not at the point of rotation, not at the pivot, not at this point right here, causes rotation. Just like acceleration is how we measure the change in something's motion, we can apply that linearly and rotationally. So here we've got King Kong. He's going to apply a force to this bridge, not through the center of mass, not through the point of rotation as we've done all year, and that's going to cause that bridge to rotate. Okay, and you can see how fast or how slow it's rotating. It's actually accelerating in that rotation. If I cause him to have a bigger force on there now, and I hit go, you can see it rotates at a higher part because it has a higher torque, a higher value. If I go even larger on the force, that's as large as I can go, I create a larger torque and I create a larger acceleration. If I move him out further, I create even a larger torque and I get even a larger rotational acceleration. It's very analogous to net force causes linear acceleration, net torque causes angular acceleration. If I move him closer to the point of rotation, now perpendicularly he's only 16 meters from that point, and I hit it, a lot less torque, because the torque is the force that he's applying, in this case 1.5 times 10 to the 5th newtons, and how far he is from it, 16. Let's make it easier numbers for you. Let's put them out here at, oh, they won't let me, at 22. Bring this down to 1, and you can see that it's 22 meters times 1 times 10 to the 5th newtons, and that's what is producing that torque. Okay, so bringing that out, now what are we going to really use this idea of torque for? For static equilibrium. Here from our equation sheet are the conditions of static equilibrium. The sum of the forces must equal 0. That is what makes it an equilibrium. If there's no net force, there's no linear acceleration. And static part, and the other part of equilibrium, is that the sum of the torques equals 0. Equilibrium means not changing. So if there's no linear acceleration because there's no linear net force, and there's no rotational acceleration because there's no net torque, if those conditions are met, it's an equilibrium. We're going to go one step further and have static equilibrium. Static means not moving. So everything we're going to look at not only is not changing its motion, but it's also not moving. So if we look at something here like this balance beam, I don't feel like playing with bricks. Let's play with people. Let's put if a 20 kilogram kid sits on one side of it, it's going to rotate. Well, if it rotated, that meant it had a net torque on it. And the reason that it has a net torque is he's producing a force of, let's see, 20 kilograms, 10 meters, 200 newtons out here, not at the pivot. If I move him in and have him sit right on the pivot, oh, won't it let me? It won't let me. But if he was to sit right on the pivot, he wouldn't be producing a torque. The further out he is, the more torque he produces, and you can see the more quicker it goes down. If I balance him with another kid of 20 and put him the exact same distance, I'm in static equilibrium. I have no net torque because I have a torque here, and that's producing what's called a counterclockwise torque, because I take, and I think about it, the way I think about it is I take and hold a pencil, and I hold it here at my pivot, and then I push down on it. And by pushing down on it over here, it will cause this whole thing to rotate. If I remove him, see? Caused it to rotate that way. Now, whoops, come on, get out here. The guy over here on our right is producing a clockwise torque. And remember, it's how far he is from the pivot, that straight line multiplied by his force here. So if I remove him, it moved clockwise. Alright, so they're producing clockwise and counterclockwise torques. Right now they're balanced, and that's the big part. I can go in here and I can throw in, let's move this guy over to here, and let's put this guy. Now he is 2 units away, and 80 kilograms, so 160 units of torque. These guys are 1, 2, let's move him to 3, and we'll move him to 4. 4 times 20 is 80. 3 times 20 is 60. 80 plus 60 is 140. My prediction is it's going to move the direction of this guy, because the bigger guy, because he's producing more torque, and it is. I would need to, let's add another kid in here. Too much. Let's move him in a little bit. Whoops, he ran away. And now he's producing that 2 times 80, that 160 units of torque. He's producing 20. He's producing 60, so that's 80. And he's producing 80. 80 and 80 is 160. The same torque is balanced there. We can look at lots of examples like this. Okay? Now the other thing is, for the net forces to be equal, you would need the normal force up from this hinge to balance it. If we look at some other examples, here we have a bar with really no mass and a load on it, supported by these two supports. As we move this, you can see how the force changes, because it always wants to meet those conditions of the sum of the torques and the sum of the forces equals 0. We will look at this in class with a lot of free body examples if you pick to do the demonstration. Here we have the same idea, but now we can move our supports. Look what happens when I pull this support in. Notice how the forces get more and more, and they're down over here, because to produce that net torque, I need a force up here, I have a force down here, and I need another force down there. If I get right here, notice no force over here. This is kind of interesting as we come here and we look at something that's balanced, like a mobile. And what I can do here is, I have these controls. I can move where my masses are, but notice right out here, my net force down, I have 50 G's down and 50 G's down, so I have 100 G's up. As I move this in, my mass over here has to get less to keep that net torque 0, and my overall force upwards here gets less also. It's this whole idea that I have to meet those two conditions. I have to meet the conditions that the net force and the net torque are 0 in all cases. If they come out of that case, then it's not in static equilibrium. Remember, static equilibrium, not moving and not accelerating. An interesting way to look at this is if I look at this blue and this green thing here, box here, and I know I'm running short on time, because the green is twice as far from the pivot point as the blue, it must have a mass, a weight that is half as much. If I do this again, now the weight of the red and the orange must add up to the weight of the green before. And again, the orange is twice as far from the pivot as the red, so the orange is going to have half the weight as the red. And I can keep going down in here if I keep those ratios. Even if I don't, I can do it. It's an interesting problem. You'll see something like it in class. One of the cooler ones here, I think, is this one, which is a little bit hard to see. But picture that I have my hand here, and the red is the force on my pinky, and the red on the right is the force on my pinky. The red on the other side is the force on my index finger. Look at how those forces change as I move from the center of this rod and back in. Alright, So the most important thing here isn't King Kong. The most important thing is that the condition for static equilibrium is that the sum of the forces equals 0 and the sum of the torques equals 0. Alright, I will see you in class. Have a good one.